Aside from pilotage and dead reckoning, other forms of navigation are also available to pilots through the use of electronic navigational aids, or nav aids for short. These systems transmit signals to aircraft through radio waves and tell pilots where they are and where to go. Before we get into what these systems are and how they work, we first need to review radio waves and antennas. Radio waves are a type of electromagnetic radiation. Artificially generated radio waves are used for fixed and mobile communication, broadcasting, radar, computer networks, and of course, navigation. These artificially generated radio waves are created from antennas. Antennas convert the electric current of a signal into a radio wave, so it can travel through space to a receiving antenna, which then converts it back into an electric current to be used by a receiver. The antennas on an airplane are all different sizes and shapes. This is because they receive or transmit different types of radio waves. There are 3 different types of waves, each with different characteristics. They are ground waves, sky waves, and space waves. Ground waves are lower frequency waves that travel close to the surface of the Earth and will, in fact, follow the curvature of the Earth. The lower the frequency of a wave, the further the signal will be able to travel. These ground waves travel reliably and predictably along the same route day after day, not being influenced by outside factors. Sky waves are higher frequency waves that can also travel for long distances. But instead of following the curvature of the Earth, the waves are refracted or bent by the ionosphere and sent back down to Earth. Using sky waves, high-frequency radios can send messages across oceans using only 50 to 100 watts of power. Space waves consist of very high-frequency waves, or higher, that neither bend nor refract. These waves travel in a straight line, passing through the ionosphere, and allow navigation from space. Most major navigation systems these days operate with signals broadcasting as space waves. Objects between the transmitter and receiver may reflect and block the signal. This means that the waves have to have line of sight between the two for the signal to be received. For aircraft, the airplane has to be within line of sight of the navigational aid in order for the system to work. One of the oldest types of nav aids still in use today is called the non-directional radio beacon, or NDB. While NDBs are not as common in the United States as they used to be, they are still used in other countries around the world. An NDB is simply just a ground-based AM radio transmitter that transmits radio waves in all directions. In the United States, these NDBs operate on the frequency range of 190 to 535 kHz. Because NDBs operate in this low to medium frequency band, they are not subjected to the line-of-sight limitations of space waves. To navigate via NDBs, pilots need to have installed in their aircraft an automatic direction finder, or ADF. The face of an ADF contains a needle that points to the relative bearing of the NDB. The relative bearing is the number of degrees measured clockwise between the aircraft's heading and the direction from which the bearing is taken from. You can use this simple formula to calculate the magnetic bearing to the station. Magnetic heading plus relative bearing equals magnetic bearing. For example, if your airplane is flying a heading of 030 and the ADF is indicating a relative bearing of 120, then that means that the NDB is at a relative bearing of 150 degrees. If you wanted to fly towards the NDB, 150 would be the initial heading to turn to. When flying directly toward the NDB, the needle will look like this, pointed straight up at the NDB station. Once crossing over it, the needle will reverse direction, but still point at the NDB as you fly away from it. It is possible to track both towards and away from an NDB station. This sounds really easy, right? Just keep the needle straight up and you'll fly right towards the station. Well, in a no-wind situation, that would probably be just fine. However, most of the time there is, in fact, wind. If a pilot were to keep the needle straight up on a windy day as they were navigating, they'd be doing a procedure called homing. Homing is not a recommended procedure to follow, as you would not be flying in a straight line. Instead of homing, tracking should be used to fly from station to station in a straight line. Tracking involves compensating for the wind by turning slightly into the wind and thereby staying on course. When you are on course and tracking to the station, the airplane's wind correction angle should equal the number of degrees the ADF is deflected from straight up. NDBs can be spotted on sectional charts with this magenta-colored symbol. In the vicinity of the symbol, you will find a box containing the name of the NDB, frequency, ID, and associated Morse code. Before you can actually navigate via an NDB, you need to tune and identify the desired station. Tuning in a station is pretty easy. Just look up the frequency on your chart and enter it into your receiver. After it's entered, we need to confirm that we are receiving the correct station and that it is operational. As part of an NDB's transmission, they'll send out their ID in Morse code format. We, the pilots, must listen to the Morse code and verify that it matches what's printed on our chart. After we've identified the station, we can use it for navigation. However, since there is no flag on the instrument to advise us whether or not it is operating properly, we must continue to monitor the Morse code for as long as we intend on using the station. Luckily, we can turn down the volume so it's not as obnoxious. There are 4 different classes of NDBs. They all operate on the same principles, but the different classes contrast in how far away their signal can be reached. The weakest of all NDBs is the compass locator. This low-powered NDB uses less than 25 watts of power, giving it a range of only 15 nautical miles. The other 3 classes are labeled as medium-high, high, and high-high, with each offering progressively larger ranges. To receive a signal from an NDB, the aircraft's ADF is able to determine the relative bearing from the aircraft to the NDB station. This is accomplished through the use of 2 antennas on board the aircraft, one being the loop antenna, the other being the sense antenna. The loop antenna is a directional antenna containing 2 or more stationary loops of wire. Looking at just one loop, if radio waves hit the loop in any direction other than directly perpendicular, a voltage will be induced over the antenna. By using multiple loops, oriented in different headings, the system can deduce down to 2 possible headings that the signal is coming from, both 180 degrees apart. To remove this ambiguity, the sense antenna is also used. This antenna, which is more or less just a straight wire, looks at the electrical field of the signal, receiving an identical signal from all directions. Looking at the phase of the signal and not the amplitude, the ADF receiver compares the sense antenna signal with the loop antenna and is able to remove the ambiguity and deduce the relative bearing of the NDB station. Now, before you start relying on NDBs for navigation, you should be aware of its limitations. The first of many errors is called the thunderstorm effect. During a thunderstorm, the ADF needle will be temporarily deflected towards the lightning strikes instead of the NDB. Next is the night effect, where NDB signals can be refracted by the ionosphere and return as sky waves. This effect is largest during the dawn and dusk hours. This can cause interference with distant NDB stations. Mountains can also have an effect on the NDB signal as they can reflect the NDB signal. Finally, there's the coastal effect. As the airplane is flying across a coastline, the ADF needle will bend slightly towards the coastline when crossing it at an angle. All of these errors result in erroneous bearing information which affects the ADF needle. Since the pilot has to monitor the NDB Morse code, hearing any static on that frequency, along with the ADF needle acting erratically, are 2 indicators that there may be an error in what you are receiving. While NDBs are a dying technology, our next NavAid is still very much alive and much more common in the National Airspace System. This type of NavAid is called a Very High Frequency Omnidirectional Range, also known as a VOR. The typical VOR is usually white and resembles a big bowling pin. However, other types of VORs exist that look much different. Since VORs operate within the frequency band of 108 to 117.95 MHz, they fall into the space wave spectrum. This does allow for relatively interference-free navigation. However, reception is limited to line of sight, which prevents a pilot from receiving a signal when at low altitudes or in mountainous terrain. VORs are oriented to magnetic north and transmit radial information outward in every direction, similar to spokes on a bicycle. Technically speaking, there are an infinite number of radials being broadcast out, but for simplicity, it is said that only 360 radials are used. In the airplane, the VOR indicator consists of three vital parts: the course deflection indicator, or CDI, the to-from indicator, and the omni-bearing selector, or OBS. The OBS knob is used to choose the course, or radial, that you'd like to reference. The to-from flag will tell you whether the radial selected will take you toward the VOR or away from it. And finally, the CDI tells you how far off you are from the center of the course in degrees. Now you may be asking yourself, "Self, what's the difference between a radial and a course?" Well, they are really the same thing. However, when flying, radials are directed away from the station, whereas courses are directed toward the station. So, when you fly away from a station, you want to follow a radial. When you fly toward a station, you want to follow a course. The reason for the distinction is because the VOR indicator, in its old-school fashion, does not know what the aircraft's heading is. Let's say you are directly south of the VOR flying northbound. You could dial in either the 180-degree radial from or the 360-degree course to into the OBS, and both will tell you that you are on course. However, if you start drifting to the west, you'd get two different indications on your instrument. The instance where you have 360 degrees to selected will indicate that you are left of center. However, if you had 180 degrees from selected, the instrument will actually indicate that you are right of center. This type of situation is called reverse sensing. If you were not aware that you had mistakenly entered the reciprocal radial into the instrument, the more you tried to correct toward the center, the further off course you would actually get. Modern-day avionics, like the Garmin G1000, use a horizontal situation indicator, or HSI, instead of the old standalone instruments. HSIs merge your heading and navigation into one instrument, and because of that, does not succumb to reverse sensing, at least with VORs. However, a pilot navigating with an HSI should still always dial in the appropriate radial or course, because if by chance there was a failure with the instrument and it no longer synced with your heading, you would not want to suddenly encounter reverse sensing. Since a VOR's radials emit out like spokes on a bicycle, the closer the pilot flies to the VOR, the more sensitive the instrument gets. Let's again say that we are south of the VOR on the 180 radial, flying northbound. We set the OBS to 360 degrees, and we get a to indication. The closer we get to the station, the more sensitive the needle gets, but the indication will continue to show to. As you pass over the top of the VOR, you enter a zone called the cone of confusion. The cone of confusion is the area above the VOR where the airplane does not get a clear signal. The to-from indicator will go to the off position because the receiver can't quite tell where you are. As you fly away from the VOR, the receiver gets the signal again and the flag flips to a from indication. Now, you can track the 360-degree radial from the VOR and continue flying northbound, tracking the radial away from the station. If at any time you want to figure out where you are in relation to a VOR, all you need to do is find what radial you are on. That means that on your indicator, you need a centered CDI needle and a from flag. Simply keep rotating the OBS knob until the CDI centers. If by chance it's centered with a to flag, you are on the reciprocal radial. You need to rotate the OBS 180 degrees left or right. It will center once again, this time with a from flag. So, by using one VOR, you would know where you are in relation to that VOR. However, you don't know at what point you are along that specific radial. For that, you'd need either distance measuring equipment, or DME, or a second VOR. The DME will tell you how far from the VOR you are, pinpointing your location. Two VORs can accomplish the same thing through a process called triangulation. To triangulate your position, pick two VORs that are near you and tune in their respective frequencies. Now, simply center both needles with from flags to find the radials. Use a sectional chart to draw the radials out. The two radials should intersect, indicating your current location. Before any flight that you intend on using your VOR receiver, you should make sure it works. FAA regulations require you to check your VOR equipment every 30 days for IFR operations. It's not required for VFR operations, but it's a good idea to test it anyway. When pilots perform a VOR check, a record of it is kept in the airplane. This log contains the date of the check, the location of the check, any bearing errors encountered during the check, and finally, the pilot's signature. Keep in mind that before you actually rely on a particular VOR for navigation, you need to make sure you have the correct VOR tuned in. This is accomplished by identifying the VOR. Just like in NDB, VORs transmit out three-letter identifications in Morse code. After a pilot tunes in a VOR, they need to listen to that VOR's audio transmission and make sure the Morse code matches what it's supposed to be. Pilots do not, however, need to know Morse code. All they have to do is match the audio with the dots and dashes printed on the sectional chart for that station. Unlike an NDB, pilots do not need to continually monitor the audio of a VOR. Once they have identified the station, they can turn the audio off. If the VOR was inoperative, the to from flag would show off. As part of another convenience of today's advanced avionics packages, systems like the G1000 can identify a VOR for you. Once you enter the frequency into your navigational radio, the G1000 displays the VOR's identification next to it. If that ID matches what's on the sectional, you have the right station tuned in. You do not need to listen to the Morse code, unless you want to, of course. Just like with NDBs, there are different classes of VOR, each with their own service volumes. VORs have a power output necessary to provide coverage within their assigned operational service volume. There are three service volumes that a VOR can have: terminal, low, and high. A terminal VOR is one usually located on an airport and is a lower powered VOR. It has a range of 25 nautical miles and reaches an altitude of 12,000 feet AGL. A low VOR is more powerful and has a range of 40 nautical miles and reaches an altitude of 18,000 feet AGL. And finally, there's the high VOR. This VOR is used to build the high-altitude airways that exist from 18,000 feet and above. This VOR is higher powered and has many layers to it. The first is from the surface up to 14,500 feet AGL and has a range of 40 nautical miles. The next layer is from 14,500 feet to 18,000 feet and a range of 100 miles. Above that is a layer from 18,000 feet to 45,000 feet and a range of 130 miles. And finally, the top layer goes from 45,000 feet to 60,000 feet and has a range of 100 miles. The rounded shape at the bottom of these service volumes is depicting the line of sight characteristics of the VOR. The way to tell what kind of service volume a VOR has is to check the chart supplement and look next to the VOR name for the symbol in parentheses. VORs are shown on a sectional chart with this symbol, surrounded by a compass rose. This helps pilots visualize and draw out radials for their flight planning. Just like with NDBs, in the vicinity of a VOR is a box of information relating to that station. It includes the same pertinent information as an NDB would have. Sometimes VORs have distance measuring equipment, or DME, as well, and will be shown by this symbol. The third and final way a VOR is shown on the chart is when it is co-located with the military TACAN. This VOR is then called a VORTAC. A TACAN is just the military equivalent to a VOR system. You may also notice certain radials being drawn on the sectional connecting different VORs together. These are known as Victor Airways and serve as predefined low-altitude routes that pilots can use to navigate along. So now that we've covered all that, let's go over how a VOR actually works. Remember that a radio wave looks like a sine curve. If you have ever taken a trigonometry class, you might remember that the sine wave has some key points: 0 degrees, 90 degrees, 180 degrees, 270 degrees, and it starts over again at 360 degrees. The VOR uses this concept to operate. The VOR emits two signals, a reference phase and a variable phase. The reference phase emits outwards in all directions simultaneously. The variable phase emits outward in a rotating fashion similar to a lighthouse. This would be a fast lighthouse rotating around 30 times a second. Older VORs were mechanically rotated. Now they are scanned electronically to achieve the same result with no moving parts. As the variable phase signal rotates around the VOR, the signal will become phase shifted from the reference phase. The two signals are detected by the aircraft's VOR receiver and then compared to determine the phase angle between them. So at 90 degrees, the two waves are phase shifted 90 degrees apart. The phase angle is equal to the direction from the station to the airplane. So this airplane is on the 090 degree radial from the VOR. The same idea is true at the 180 radial and the 270 degree radial. The two signals are phase shifted and the airplane receivers can detect this difference. As previously mentioned, one of the ways pilots get distance information is through something called Distance Measuring Equipment, or DME. This system operates on frequencies in the UHF spectrum between 962 MHz and 1213 MHz. Similar to other systems, DME emits a Morse code ID every 30 seconds to indicate that it is operating correctly. The range of DME is 199 nautical miles, but it only serves the closest 100 aircraft. They are also subject to line-of-sight restrictions, just like a VOR. To obtain distance from a station, your aircraft's DME receiver first transmits a signal to the station. The station then replies back. The aircraft's receiver then measures the time it took to complete the trip and converts that into distance. Because of that, DME gives the pilot something called a slant range distance. This means that the distance shown is actually going to be the exact distance to the DME station, not the distance across the ground. So an airplane at 3,000 feet might get a DME distance of 0.6 nautical miles, when in fact the plane is 0.5 nautical miles away from the DME. The effect worsens at higher altitudes. In fact, if you fly over a VOR at 6,000 feet, even though you were right on top of it, the DME will tell you that you are 1 nautical mile away from it. The Global Positioning System, or GPS, is the United States version of a Global Navigation Satellite System, GNSS. The space-based navigation system can trace its roots back to the 70s when testing began. However, the system became fully operational back in 1995. The GPS system consists of 3 elements: space, control, and user. The space element consists of a minimum of 24 satellites and 6 orbital planes around the Earth. There are usually closer to 30 GPS satellites in orbit at any time. These satellites are in a medium Earth orbit at 10,900 nautical miles above the Earth. At this distance, they orbit the Earth every 12 hours, or twice a day, meaning they are not in geostationary orbit like communication and weather satellites. At this orbit, they travel roughly 7,000 miles per hour, and at an inclination angle of 55 degrees from the equator. This is important because it allows 5 satellites to remain in view at all times from anywhere on Earth, except at the poles. Each satellite is built to last about 10 years, with replacements built and launched as needed to keep the system running smoothly. GPS satellites are powered by solar energy, but have backup batteries on board to keep them running during periods of solar eclipses. In addition, small rocket boosters are located on each satellite and are used to keep them flying in the correct orbit. Finally, each satellite contains 2 or 3 atomic clocks, which are the key components to getting your position. The control element consists of ground-based monitoring stations, a master control station, and ground antennas around the world. The goal of the control element is to ensure the accuracy of the GPS satellite positions and the accuracy of the atomic clocks on board. The master control station gets data from monitoring stations pertaining to errors with satellite orbits or clocks, and is able to send data and instructions to the satellites to correct for any errors detected or to move satellites back to their proper orbits. The user element consists of the combination of the antennas, receivers, and processors in the airplane that receives the signal and calculates your GPS position. There are a wide range of receivers, anywhere from handheld devices to panel-mounted to full flight deck systems, but they all perform the same calculations to give you your position, and each has their own limitations that the pilot must be aware of before using them for navigation purposes. Each GPS satellite transmits the GPS signal in the microwave range. The two primary signals are called the L1 and L2 frequencies. The L1 frequency transmits at 1,575.42 MHz and is for civilian use. The L2 frequency transmits on 1,227.60 MHz and is encrypted for use by the military, although these frequencies are not important to know. Each signal transmits a course acquisition code that contains three parts. First, a pseudo-random code, which is an ID code that identifies the transmitting satellite. This also prevents something called spoofing, which in simple terms prevents anyone from interfering with the GPS signal. Second is something called the ephemeris data, which is describing where each GPS satellite should be in orbit at any given time. And third is the almanac data, the current date and time, and the status of the satellite, whether healthy or unhealthy. The entire GPS signal takes approximately 30 seconds to receive. The idea of how the GPS works is based on a principle called pseudo-ranging. This is the name for the process that allows us to calculate our distance, not by actually measuring distance, but calculating it with a time calculation. This is done using the same formula from dead reckoning. Rate times time equals distance. Radio waves travel at the speed of light, which is 186,000 miles per second. The GPS satellite sends a signal to the airplane that has the time the signal was sent. The receiver can compare the time the signal was sent to the time the receiver received the signal. Since we know the speed of the signal and the time it took to get from the satellite to the receiver, we can calculate the distance from the satellite to the airplane. So the GPS signal that is sent out really is more like, I am satellite X, my position is Y, and this information was sent at time Z. There is one problem though. This means that we are approximately 10,900 miles away from the satellite in all directions, essentially making a sphere that we are on. In order to pinpoint our location, we need to use more satellites. By adding a second satellite, there are now two spheres that intersect. This makes a circle of where we could be. A circle contains an infinite number of points, so we need to add a third satellite to get our position. By adding a third satellite, the sphere of our possible locations from the third satellite intersects the circle in two locations, one on Earth and one in space. By eliminating the location in space, we know our 2D location. In order to get a 3D location, a fourth satellite is necessary to remove any ambiguity in the position. The GPS satellite constellation is designed to make at least 5 satellites in view at all times, and most of the time there are several more received. If we receive more signals from satellites other than the 4 necessary to get our 3D position, the GPS receiver will use the additional signals in its position calculation and give the pilot an even more precise location. Now that we know our 3D position, we need to check the accuracy of the GPS signals. In order to do this, our GPS receiver calculates something called Receiver Autonomous Integrity Monitoring, or RAIM. This is the system the receiver uses to verify the usability of the received GPS signals, which warns the pilot of malfunctions in the navigation system. In order for the receiver to calculate RAIM, we need to receive at least 5 satellites. If RAIM is not available, the pilot will receive a message from the GPS to warn him or her that there may be some error in the GPS position. RAIM outages may occur when there are an insufficient number of GPS satellites, or there is an unsuitable satellite geometry, either of which can cause the error in the position to become too large. Just like every other navigational system, there are several GPS errors that a pilot can experience while flying. The first is any time there are fewer than 24 operational satellites, which may result in a lack of adequate GPS signal. Next, any time the antennas on the aircraft are blocked from receiving the signal by high terrain, such as in a valley. Or any time the aircraft's GPS antenna is shadowed by the aircraft structure, like when the aircraft is banked. Some other errors that can occur are harmonic interference from VHF transmitting devices, satellite atomic clock inaccuracies, receiver or processor errors, or even a bounced or multipath signal reflected from hard objects. There can also be errors caused by the signal traveling through the ionosphere and troposphere, which can cause a delay in the signal. Additionally, sometimes there are satellite data transmission errors, which may cause small position errors or momentary loss of the GPS signal. Finally, there was an error called selective availability. This is an error caused by the U.S. Department of Defense that can purposely cause error in GPS signals. This error was discontinued on May 1, 2000, but may be reinstated at any point in the future that the Department of Defense finds it necessary. So, to sum up, all of these errors, when added together, equal an error of plus or minus 15 meters, or roughly 45 feet. When selective availability was turned on, the error was plus or minus 100 meters, or about 300 feet. The less error we have, the better. To improve the accuracy, integrity, and availability of GPS signals, something called Wide Area Augmentation System, or WAAS, was designed. WAAS works so well that the location error is a mere 10 feet or so. As the GPS signal reaches Earth, it is received and monitored by ground-based wide area reference stations. These stations monitor the GPS signal and relay the data to a wide area master station. At the master station, a correction to the GPS signal is computed. A correction message is prepared and uplinked to one of the geostationary WAAS satellites via a ground uplink, and then broadcast on the same L1 frequency as the regular GPS signal. Any GPS receiver that is also WAAS capable will be able to receive the correction message. The receiver will then apply this correction into its GPS position calculation and display to pilots an even more accurate position. The WAAS satellites are in an ideal position for their geostationary orbit, allowing them to cover a large portion of the Earth. To take full advantage of their location, the WAAS satellites will also act as regular GPS satellites. In essence, there are always an additional 2 or 3 regular GPS signals available to pilots across the United States.